Conveniently, radioactive decay all follows a first-order decay reaction. So if we have some strontium-90, mass of strontium-90 on our y-axis in this plot, and time in x-axis, you'll see that the half-life is 28.8 years. That's something that has been determined. So if we start with 10 grams of strontium-90, after 28.8 years, we'll have 5 grams. After an additional 28.8 years, so almost 60 years, we'll have 2.5 grams, and so on and so forth. And recall that each one of these time blocks of 28.8 years is a half-life. So this plot shows 1, 2, 3 half-lives. Again, our first order decay and half-life follows this equation, T1 half equals 0.693 over K, which is where K is the rate constant. And if we want to find a fraction of nuclei that remain after a given amount of time, we can use our first order decay rate law. We'll have natural log of the nuclei at time t over the initial amount of nuclei equals minus k times t. Now you can use the number of nuclei in mass, you could use moles, you could even use atoms or nuclei, number of nuclei, and because they're all going to be proportional. As long as you don't mix your units, this will work out. Now we use radioactive decay for a number of different reasons, but we can harness the science behind that and determine how old something is. So for instance, in carbon dating, the half-life of carbon-14, which is a radioactive isotope of carbon, is 5,730 years. Let's correct that to a more precise number, 5,730 years. And so we can determine the amount of carbon-14 in an object to figure out how old it is. And we're limited to a certain age range, up to about 50,000 years old. And beyond that, there's just so little radioactivity that you can't really measure it. Now, this only works, carbon dating only works for things that were living. So plants, animals, things like that. But other isotopes can be used to date inanimate objects or things that weren't living. The ratio of uranium-238 to lead-206 can be used to date rocks. This figure takes us through the process of how carbon-14 exists in the atmosphere, how it's produced, and how it's consumed by plants and animals, and what that means. So basically what happens is cosmic rays collide with atoms in the atmosphere and create neutrons. Those neutrons then collide with nitrogen-14 to produce carbon-14 and a proton. This carbon-14 can combine with oxygen to create carbon dioxide, and as we know, plants use carbon dioxide in photosynthesis, and then animals can take in that carbon dioxide through eating plants, and other animals that don't eat plants will eat the animals that had the carbon-14, etc. Okay. Once an organism dies, the intake of carbon-14 stops. Okay, that is the starting point for determining the amount of carbon-14 in that organism, and then thereby dating it. So once the animal stops taking in carbon-14, the carbon-14 concentration decreases through beta emission, as shown in this reaction here. Eventually, after many, many years, you get an immeasurable amount of carbon-14. There's an additional video that I'd like you to watch. It's on the Carmen page, so I'll let someone else explain carbon dating and all of the really cool chemistry that goes on behind that. There's a lot of things that you'll recall hearing previously in our course, including some electrochemistry. So I think you'll find it very interesting.